Okay, let's take a look at number 68 here. It's a homework problem, sometimes difficult for students, so let's do a video solution. A fugitive tries to hop a freight train traveling at a constant speed of 6 meters per second. Just as the empty boxcar passes him, the fugitive starts from rest, accelerates at a rate of 4 meters per second squared to his maximum speed of 8 meters per second. How long does it take for him to catch up to the boxcar? And what is the distance traveled to reach that car? Now, because there's a lot going on here, I'm going to go ahead and start by just drawing a couple of pictures to try to make sense of the situation. I'm going to start with a dot diagram and then draw a couple of graphs to try to make sense of what's happening. So, boxcar, let's draw that using green, traveling at a constant speed. So a dot diagram for that would just show equal spacing here. And we know that that velocity is given to us as 6 meters per second. Okay, the fugitive, let's go with red for that. Fugitive is starting from rest and is accelerating at a rate of 4 meters per second squared. So by the time, let's just say that this is his maximum speed, by the time we get to his maximum speed, that's going to be greater than 6 meters per second. And that velocity is just simply increasing. We do have an acceleration vector here. I'm not going to go ahead and draw that here, but once he gets to maximum velocity, we know that now his dot diagram would stay with dots that are equally spaced. Now, certainly this problem would be fairly easy if he was able to get up to the boxcar and still not reach his maximum speed, but I suspect, looking at this problem, that by the time he gets up to his maximum speed, the boxcar will have traveled further away, and he still has to continue to run to catch up to it. So that we have a multi-part problem here. Let's go ahead and draw a couple of graphs to help us see what this might look like if we were to construct position and velocity graphs. And again, what I'm doing here is I'm just using some tools that we have available to us to help us figure out how to solve a problem when it's a little bit more complex. Let's go ahead and use some color coding. The boxcar is moving at a constant speed. And both the position and velocity graphs are pretty straightforward for that. We know that that's 6 meters per second, and the slope of that would be 6 meters per second as well. Now, let's do the fugitive. The fugitive is starting from rest and accelerating. At some point, they're going to start to reach a maximum speed. Now, you can see that it's a little bit steeper there than 6 meters per second, but at that point in time, let's just call that some value t that we'll probably eventually calculate. Now the graph no longer is curved, now it's going to continue on in a straight line fashion. This, of course, is the point at which the fugitive catches up to the boxcar. We'd like to know how long that takes. So this is the eventual answer that we're looking for. That's the t that we're looking for. And we're also looking for how far. Okay, so that's those 2 points are the answers to our question. Now, let's continue on with the velocity time graph down here. At some point in time, the fugitive will stop accelerating. And let's say that that is the point at which that occurs. And we know that that value is 8 meters per second. Okay, that looks good. Now, if I did this correctly, and if the fugitive is actually behind the boxcar still by the time he gets up to his maximum speed, we can see that this graph is actually showing that pretty well, that at this particular point, if I were to look at the area underneath the velocity time graph for the fugitive, I see that that's actually a smaller area than the area underneath the velocity time graph for the boxcar. And so I tried to draw this somewhat correct, at least qualitatively, and certainly we can see that by the time we get to this point, over here, the idea is that the area underneath this oddly shaped red figure here is actually now the same area as that rectangle. So again, area underneath the velocity time graph represents displacement. I'd like to find out what that value is for t, and of course how far they've traveled. So there we go. We've got a picture of what's going on with dot diagrams. We have some graphs, and that might help us sort of inform our solution, how we're going to try this. I'm going to start with part 1 here. And I'm going to try to calculate the time to get to maximum velocity for that fugitive. So how long and how far for V max. So how long does it take for the fugitive to get up to that speed, and how far has he traveled? Okay, seems like a fairly straightforward question for us to answer. Let's see, if the acceleration is 4 meters per second and his maximum speed is 8 meters per second, that's not too hard to do. 8 meters per second, accelerating at 4 meters per second means that it will take 2 seconds to reach maximum speed. So this value right here is 2. And let's determine how far. Well, how far can be found with this equation. Two squared is 4. 4 times 4 is 16. Take half of that is 8 meters. So at this particular point, he's 8 meters from the starting point. Let's determine, for part 2, how far the boxcar has moved during that time. I'd like to see where this boxcar is. So we can do that with just another equation for that particular car's motion. And since it's moving at a constant speed, and go ahead and use that equation. 6 meters per second for 2 seconds means that the boxcar has traveled out 12 meters. Okay, so at this point in time, the fugitive is up to his maximum speed. The boxcar is out 4 meters ahead of him. And how long will it take for him to catch up to the boxcar if the relative velocity between these two is 2 meters per second? After 1 second of time, we'll see that the fugitive will have traveled 8 meters, and this car would have traveled 6 meters, so he would have made up 2 meters. After another second of time, he will have traveled another 8 meters, and this car would have traveled 6 meters. He would have caught up to that boxcar after 2 more seconds. So part 3 on this, before I actually answer any of those questions, is how long to catch up. When velocities are maximum. And again, I talked about a relative velocity there. Let's go ahead and write that just using some of our math here. The relative velocity, the velocity that between those two objects, is just 8 minus 6 would be 2 meters per second. And how far they have to travel to be able to catch up there is 4 meters. So combining these with this basic equation, there's no acceleration at this point. If I want to calculate that time to catch up, it's just going to be delta x over that velocity, which would be 4 meters. And he's catching up at a rate of 2 meters per second. That means it will take 2 seconds for him to bridge that gap right here. So this is another 2 seconds. So the total time would be 4 seconds. And that's the answer to our first question. Letter A, how long does it take for the fugitive to catch up to the boxcar? The total time is equal to 2 seconds of acceleration plus 2 seconds of constant speed, or 4 seconds of time. Part B, how far has have these two objects traveled? Probably easiest just to use the motion for the boxcar. Delta x for the boxcar is just equal to the velocity of that boxcar times that total time. So 6 meters per second, traveling for a total of 4 seconds, means that the boxcar and the fugitive would have traveled 24 meters during that time. There are the two answers.